Hi, I'm Mr. Miller, and this is a lesson on analyzing rational functions. So first, let's look at what is a point of discontinuity. So this is a discontinuity due to a non-permissible value of x, leaving a singular hole in the graph where the graph is otherwise continuous. So here's an example of that. We've got a function f at x. We want to find its point of discontinuity. So notice that the non-permissible value of x is that x cannot be equal to 1. And if we take this and put it in factored form, we realize that there is a factor that can divide out the x minus 1, and we're left with x plus 3. So at x equals 1, the y value would be 4 if the function were defined there. Since it's not, 1, 4 is actually a hole. So you draw a straight line here, y equals x plus 3. In other words, the y-intercept is 3, and the slope is 1, and this is a straight line. Except for the fact that at x equals 1, y equals 4, there is a hole in the graph. So it looks like this. Next, let's take a look at the graph of y equals x squared plus 2x minus 3 over x plus 1. Then we're also going to graph y equals x plus 1 and explain how it's related to the graph. All right, so again, we're going to put this in factored form. And we realize that there's no simplification here, so there's no hole. Instead, there's a vertical asymptote at x equals negative 1. Now, if we do the long division, we can go x times x plus 1 is x squared plus x. And if we subtract away, we have a remainder of x. Now we bring down the negative 3 and we do 1 times x plus 1, which gives us x plus 1. And when we subtract, there's a remainder of negative 4. So the function can be rewritten like this: x plus 1 plus negative 4 over x plus 1. So when we graph this function, what we're going to see is that it does have so this is y equals x squared plus 2x minus 3 all over x plus 1. And it's got a vertical asymptote at x equals negative 1, but it has an oblique asymptote at y equals x plus 1. And so that's the equation of the oblique asymptote, is that quotient part, not the remainder or the divisor. So quick summary. If you examine all the graphs so far we've done in 9.1 and 9.2, then you should be able to come up with some conclusions, which I'm going to share with you right now. How can you tell whether the graph of a rational function will have vertical asymptote or a point of discontinuity? So x values that make the quotient 0, or sorry, the denominator 0, will cause these discontinuities. And when the discontinuity can be factored out with a factor from the numerator, then there will be a hole. Otherwise, there will be a vertical asymptote. Next, where can you find an x-intercept? So an x-intercept will occur when y is equal to 0. These x values can be found by solving where the polynomial is equal to 0, the numerator. Y-intercepts are found when x is equal to 0. So you substitute x equals 0 in and find those y values. And the term end behavior refers to as x goes to positive and negative infinity. It's the direction the graph is going on either side. So that completes the lesson on analyzing rational functions. Thanks for watching and have a good day. Bye.